Hi everybody, welcome back. Before we begin today's lesson, we are going to review a concept we talked about in 5B1, and that is the sum and difference of two cubes. So what we want you to do, pause the video, complete the two examples, and then when you're ready to check your work, hit play and we'll see how we did. Okay, on the first example, both terms are perfect cubes and they're separated by subtraction. So there is no GCF to factor, but because they are perfect cubes, I don't need to factor out the GCF, which there is none. So first thing we want to determine is our A and B terms. So I have to ask myself, what cubed gives me 8x cubed? Well, 2 cubed gives me 8. X cubed gives me x cubed. Okay. And then what cubed gives me 27? 3. Okay, so that right there becomes our A and our B. So that becomes our A and our B. Now, if you remember the formula from 5B1, the formula for subtraction was A minus B times A squared plus AB plus B squared. Okay, so following this formula with A and B, we just get 2x minus 3. And then our second parentheses, the trinomial, is A squared, so 4x squared, plus A times B, 2x times 3, 6x, plus B squared, which is 9. Now, if you've done this correctly, A, the trinomial will not factor further, and B, if you did put that into quadratic form, you would get an imaginary as the trinomial. Let's look at number 2. Okay, number 2 is 5x cubed plus 320. Now, I know 5 is not a perfect cube, and I know 320 is not a perfect cube, but I bet I can factor that 5 out. And when I do, on the inside, that gives me x cubed plus 64, which are both perfect cubes. So I need to break this up into A and B. Well, x cubed gives me x cubed. 4 cubed gives me 64. So that becomes 5 times x cubed plus 4 cubed. Now, that becomes our A and our B. And if you remember correctly, the formula for A cubed plus B cubed was A plus B times A squared minus AB plus B squared. So using that formula, I end up with 5 times x plus 4 times x squared minus 4x plus 16. Now, don't forget that GCF on the outside, because if you do, it will be wrong, because then it won't multiply back to make 5x cubed plus 320. Okay, so today we're going to take what we learned in 5B.1 a little bit further today. Today we're going to talk about graphing polynomial functions. And within that graphing, we're going to talk about zeros, linear factors, how we solve polynomial equations. We're going to kind of dip our toes into that pool just a little bit. But basically, we're going to take what we talked about on 5B1. Remember on 5B1 when we talked about I said draw a possible quartic function, and we kind of drew what it might look like. Well, today we're going to be able to draw and graph exactly what it looks like given its attributes from the equation. So let's get started. So example 1, they want us to graph y equals x times x plus 1 times x plus 4. Now this is a 5-step process, and the 5 steps are: find your zeros, determine your end behavior, determine your y-intercept, find your relative max and min, and then graph. Okay, so roots, end behavior, y-intercept, relative max and min, and graph. So first step, to find the roots. We know when we find the roots, that means we make the equation equal to 0. Now, lucky for us, this is already in factored form. So we just have to set the factors equal to 0 to find the roots. However, if it was in standard form, we'd need to factor it and then set each factor equal to 0. But we don't have to do that this time. So we're going to say, okay, x equals 0. And the next one, x plus 1 equals 0. X equals negative 1. Then x plus 4 equals 0. X equals negative 4. Now, because I said roots, I can get away with saying x equals 0 instead of 0, 0 like I would for an x-intercept. However, keep in mind, SRZs, solutions, roots, zeros, they're the same thing as an x-intercept. It's just a technicality on how you call it. If you say, I'm going to find the x-intercept, then of course it would be 0, 0, negative 1, 0, negative 4, 0. Or if you just say find the roots, you can say, oh, x is equal to 0. Oh, x is equal to negative 1. And oh my goodness, x is equal to negative 4. It's just a technicality on naming. So just be cognizant of if you're writing it as a solution root 0 or an x-intercept. Okay, just a small technicality. So we've got step 1 done. We have found the roots. These are the 3 places where my graph is going to touch the x-axis. Okay. Step 2, determine end behavior. Well, if you remember, end behavior is determined by the leading term in standard form. So if your equation is in standard form, this is done for you. If it's not, you gotta put it in standard form. So I have to multiply this together. Now trust me, I have many, many, many years of experience on this, okay? It is easier to multiply the 2 binomials first and then do your distribution at the end versus trying to multiply by x and then multiplying that together, okay? You're going to make less mistakes if you multiply the 2 binomials together. Now you can do double distribution, you can do FOIL, you can do box, whatever works for you. So when I multiply those 2 binomials together, I get x times x squared plus 5x plus 4. Then I distribute the x to everything inside. And I end up with x cubed plus 5x squared plus 4x. So now this guy is in standard form. So our leading term is x cubed. Now, because this is x cubed, I first of all know it's going to be a cubic equation. X cubed, my highest power is 3, so it's going to be a cubic equation, a cubic function. Okay, I also know that because the exponent is 3, then that means I have a maximum of 2 terms. Remember n minus 1? So 3 minus 1 is 2, so that means my graph will have at maximum 2 turns. All right, now let's talk about right behavior, because remember, we always determine right end behavior first. So right end behavior is determined from the A. Well, A equals 1 in this case. So since it equals 1, that is positive. So since it's positive, right end is going to go up. So max of 2 turns, right end up. Let's talk about left end behavior. Well, n is odd. A cubic of 3, that's an odd number. So odd, opposite, odd, opposite. So if right end is up, that means left end is opposite, which means left end goes down. Okay, so we know what's happening on the right side of the graph. We know what's happening on the left side of the graph. Let's talk about the y-intercept. So the y-intercept is where x is 0, and I get 0 times 1 times 4, which is 0. So that means my y-intercept is 0, which that makes sense. If one of my SRZs is 0, then that means my y-intercept is also 0. So that makes sense. Okay, so we've got the first 3 steps done. Let's look at step 4. Step 4 says that we have to find the relative local, which is local, relative or local, max and min. Now, here's another fun fact. We call it a relative max or min because it's not the true max or min of the graph, okay? Because these graphs are going to have many peaks and valleys, many maximums and minimums. So there's not an absolute max or an absolute min. So that's why we call them relative, because they're relative to the graph for that point. All right? So this we're going to need our graphing calculator for. Okay, we're going to need that graphing calculator. So we're going to have to use our TI. You can also do this using Desmos as well. All right, so these are the steps for the TI-84 or your graphing calculator. The first step is you are going to put the equation into y1. X times x plus 1 times x plus 4. Now I always get the question, does it matter if I use the factored form or the standard form? Here's the deal. I would always put the form that they have you start out with. So if they started you off with standard form, put the standard form. If they started you out with factored form, put the factored form. Because if you made a mistake somewhere along the way, you're going to catch it when you look at this graph. So that's why I always use the given form of the equation. So I put that into y1. I then look at my graph. I'm like, well, can I see the relative max and min? And the answer is yes. I'm going to have a relative max there, and I'm going to have a relative min right there. So I can see my max and my min, so I don't need to change my window. If you could not see it, you'd want to expand your window so that you could. Okay, so we see it. So the next step is I am going to go to second trace. Second trace is going to give me the calculate feature. Okay, so you're going to go second trace. Now, does it matter if you find the relative max or the relative min first? The answer is no, it does not. Okay, but I'm going to start with the maximum because it left to right. The maximum occurs first. So you're going to pick option 4. Then what you're going to do is you'll get a little cursor. Okay, now since we're finding the maximum, you'll want to move a little to the left and hit enter. Then it'll ask you for the right bound. So you'll move a little to the right. Okay, so when it says left bound, move a little bit to the left of the maximum. And then when it says right bound, move a little bit to the right. Then it's going to ask you, do you want to take a guess? Nobody's got time for guessing. We are way too busy and way too important people to be guessing on anything. So let's let the calculator do the work. So we just hit enter because we don't care about the guess. And then it will give you the maximum right down here. So here is the coordinate point of your maximum. We usually say go to the 10th place because again, you're graphing and your graph is not going to have a gazillion little tick marks in between the major ones. So we say go for the 10th place or 1 decimal place. So I get that the relative max, when I round appropriately, is negative 2.9, 6.1. I then repeat the process, but this time I'm going to pick minimum. So second trace, pick the minimum now. We're going to now find that relative minimum. So you're going to go to your graph. It's going to ask you for a left bound. That means, hey, go a little bit to the left and hit enter. Okay? Then it'll ask you for the right bound. So you move a little bit to the right and hit enter. Then it's going to ask you for a guess. Well, we do not have time to be guessing, so just hit enter. So left bound is to the left of the minimum, right bound is to the right of the minimum. Doesn't have to be a great amount as long as you're on the left and then on the right. Then hit enter for the guess, and it will give you the minimum function. So when, again, we write that as a coordinate point. So that, if we round to the 10th place, is going to be negative 0.5 and negative 0.9. Okay, so we've got our zeros, we've got our end behavior, we've got our y-intercept, we've got our relative max and mins. Now let's graph. Okay, let's graph those 4 pieces of information we found. I always plot all of my intercepts first. So I plot the x-intercept and I plot the y-intercept. And luckily in this case, one of our x-intercepts is also the y-intercept. So we're good there. All right. The next thing, if you remember, step 2 was end behavior. Step 2 was end behavior. So how do we plot the end behavior? Well, you go to the rightmost x-intercept, and that's where you put your right end behavior. So if you remember, right end was up. Okay, then you go to the leftmost intercept, and that's where you put your left end behavior. Now, if you remember back, it told me that left end was down. Okay, so step 3, well, step 1 and step 3, x-intercept and y-intercept, they kind of go together. And then we go and we plot step 4. Now, step 4 is your relative max and relative min. Now, this is the one thing that you want to label on your graph. So when you're plotting your relative max and min, it's not enough just to plot the point. So when you plot your relative max and min, you want to put the coordinate point on the graph as well. So you'll plot it, and then you'll put the XY coordinates above it. And then for the relative min, you'll plot it, and you'll put the XY coordinate below it. So it's not just enough to plot it. You will lose credit if you don't label the relative max and min. Now we connect the dots. There we go. And so that is our function, just a fancy game of connect the dots. Now it's going to ask you for increasing and decreasing intervals. Now, increasing intervals and decreasing intervals are from x to x. Okay, so increasing is where the y's are getting bigger. So from what x to what x are the y's getting bigger. Decreasing is from what x to what x are the y's getting smaller. Now, I like to think of increasing and decreasing intervals as like a roller coaster. Increasing interval is where the roller coaster car is going up, 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 up to the relative max. And then the relative max is where you gotta pause, and then you go downhill. So the minute your roller coaster starts going downhill, that's your decreasing. So roller coaster climbing up the hill, that's increasing. Roller coaster sliding down the hill, that's decreasing. So let's look. Okay, so if I go, and remember, you always read your graphs left to right. So as I come from negative infinity, I'm increasing, 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 increasing. Oh, I stop right there. So from negative infinity, because that's where that graph is headed, so from x equals negative infinity all the way up to negative 2.9, I'm increasing. Okay, now the reason we put a parentheses versus a bracket at negative 2.9 is because that point's really neither increasing nor decreasing. It's just a turning point. Okay, now let's look at what happens. From negative 2.9, my roller coaster is going downhill, and it stops right at negative 5. So at negative 2.9, it's decreasing, 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 and then it stops at negative 0.5. So that's my decreasing interval. And then lastly, from negative 5, it starts, increasing, 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 all the way up. Okay? So from negative 0.5 to positive infinity, your graph is increasing. All right, let's try another. So this one's a little bit different. They said write the equation of and graph the polynomial equation with zeros at -2, -5, and 3, and a leading coefficient of 1. So this time they did step 1 for me. They found my zeros, okay? But I still need to put it in some kind of form for an equation, okay? So in this case, since on step 1, since they already found the zeros for us, we're going to say step 1, we're going to put that into factored form. Now, if you remember back in writing the equations of a quadratic, we gave you a form. It was called factored form. It was y equals a times x minus root 1 times x minus root 2. And I told you, you want to memorize this formula, make it your best friend, because it's ultimately going to work for any polynomial. You just keep tacking on roots. So this one, it has 3 roots. So I'm going to have x minus root 1, x minus root 2, x minus root 3. Okay, you just keep adding on factors for the number of roots you have. So in this case, I only have 3. So, and I know my a, that's my leading coefficient. I know my a is 1. So I plug in the roots or the zeros, same thing, and I plug in a equals 1. Now, minus a negative is plus a positive. Minus a negative is plus a positive. And then that final one, x minus 3, is just fine. Now you're going to see I dropped the leading coefficient of 1 because we know if it's 1, it's an understood 1. Okay, so step 1, since they gave us the roots or the zeros, we just flip-flopped the tables and said, okay, we're going to put it in factored form now. If they start with factored form, then you just pull the roots out. Okay, so that step is a little bit interchangeable. All right, so factored form, we're done with that. Now, so we know the roots, that's step 1. Step 2 is determine in behavior. Well, before I can determine in behavior, I have to multiply these together. It has to be in standard form. So, again, it doesn't matter which 2 you pick to multiply together. I am like very type A personality, so I always multiply the first 2 together. So, when I multiply x plus 2 times x plus 5, I get x squared plus 7x plus 10. Then I take that trinomial and I multiply it by x minus 3. Now again, you can do double distribution or you can do the box. So x times x squared is x cubed. X times 7x, 7x squared. X times 10, 10x. Negative 3 times x squared, negative 3x squared. Negative 3 times 7x, negative 21x. And negative 3 times 10 is negative 30. Now, remember back on 5B1, we had you review multiplying polynomials. Now you know why. Okay, so we are going to combine like terms. So I have 2x squared and I have 2x's. So when I combine like terms, I get y equals x cubed plus 4x squared minus 11x minus 30. Okay, so we're in standard form. We can determine maximum number of terms. We can determine right in behavior and left in behavior. Okay, so first of all, it's a cubic. Yay! Okay, since it's a cubic, remember n minus 1 is our maximum number of terms. So 3 minus 1 is 2. So we'll have at most 2 turns. Now we determined right end. Always determine right before left. A is equal to 1. So that's positive. So that means my right end is going to go up. For left end, the n is odd. 3 is an odd number. So odd means opposite. Opposite of right, end up, is left end down. So opposite of up is down. So cool. We know maximum number of turns, we know left end, and we know right end. All right. Step 3 is we're going to find the y-intercept. Well, remember that means put 0 in for x. So 0 plus 2, 0 plus 5, 0 minus 3. 2 times 5 times negative 3 is negative 30. But because it's an intercept, we have to write it as a coordinate point. Okay, so my y-intercept is negative 30. Now I'm ready to find the relative max and the relative min. All right, now we're trying to find the relative max and min. So I put the factor form. Now you're like, why didn't you put the standard form? Well, because I was given the roots and I'm pretty sure I got the factored form right, but if I made a mistake changing it into standard, it wouldn't show it on the graph. So always start with basically the essential form of the function they gave you. So I put that into y1, then I graph, and I'm like, oh no, holy Toledo, Batman. My max and my min are going to be somewhere here. They fell off the graph. So I'm like, I need to adjust my window. So I hit the window key. Now I'm not going to change my x min or my x max because I can see basically where the x part is going to come from. It's just the y. It's the height and the kind of the low part that I can't see. So it's the y values. I know the x's are going to hit there. So I leave the x's alone, but I change my y mins and my y max. Now, this is basically trial and error. I start out with 40, so negative 40 for the y min and positive 40. So negative 40 for the y min and positive 40 for the y max. Okay, now if that didn't work, then I might try negative 50 and positive 50, or negative 60 and negative 70. Again, it's just trial and error till you get that graph to fit within your window. And for my case, negative 40 and positive 40 worked. So now I can see that I'm going to have a relative max there and a relative min. So now we're ready to find those coordinates. So again, we hit second trace, and that pulls up the calculate menu. I'm going to find the maximum first. You could find the minimum. It really doesn't matter. And remember, it's going to ask you for a right bound and a left bound. So on the right bound, I'm just going to make my cursor go a little bit to the left. And for the right bound, I'm going to make it go a little bit to the right and hit enter each time. And then they're going to ask you for a guess. I do not have time to guess. We are way too busy and way too important to worry about guessing. So I know that sounds silly, and it's meant to sound silly, but you don't have to worry about the guess. Truly, you don't. That's a waste of time. So left bound, hit enter. Right bound, go to the right, hit enter. Don't worry about the guess. Hit enter, and it will tell you that your relative max is at negative 3.7, 14.8. Now, we rinse and repeat to find the minimum. So we go second trace, we pick minimum. Then it's going to ask me to go to the left, so I pick a point to the left, and then I pick and hit enter, pick a point to the right, hit enter. Do not worry about the guess, just hit enter. And then it will tell you that your relative min is at 1, negative 36. So now we've got all 5 pieces of information that we need. So now we're ready to graph. All right, let's graph all of that information we just found. So when I think of my x-coordinates all fall between negative 10 and 10. So I don't need to change my x scale. I'm going to count my x's by 1. However, when I think about my y-coordinates, I have a relative min at negative 36. So yeah, scaling it by 1 ain't going to cut it. So I'm going to scale my y's by 10. Anytime you change the scale from 1, you need to indicate somewhere on your graph what your scale is. Do not assume that the reader of your graph knows what that scale is. You have to tell the person reading your graph what you're counting by. Okay? So I got to graph the roots. So boop, boop, boop. Okay, so we got the roots. Now we're going to talk about end behavior. So we go to our rightmost 0. Well, if I remember, right end behavior was up. And if I go to my left 0, left end behavior was down. Okay? Now I'm going to plot my y-intercept at -30. Now I'm going to plot my relative mins and maxes. Now remember, you've got to label those coordinates. If you don't label, that's bad. If you don't label the relative max and min, you're going to lose points. So make sure you do label those. Now it's just a fancy game of connect the dots. And that is what your graph looks like. Now, let's talk about increasing intervals and decreasing intervals. So remember, we read our graph left to right. So if we're coming from the left, that's negative infinity. So if I'm coming from negative infinity, I'm increasing because I'm going up, 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 hit the relative max, so I got to stop. So my first increasing interval is negative infinity to negative 3.7. Then at my relative max, my roller coaster is going up, so it's got to go down. So it's decreasing, 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 decreasing. So from negative 3.7 to 1, I'm decreasing. Now, at 1, I'm going to start climbing again. So increasing, 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 and I'm just going to keep going. So negative 3.7, 1, not negative 3.7. So at 1 to infinity, I'm increasing. So negative infinity to negative 3.7, increasing. Negative 3.7 to 1, decreasing. And then 1 to infinity, remember these are x intervals, increasing again. All right, let's talk about multiplicity. Multiplicity sounds really difficult, but it's not. Basically, multiplicity is the number of times an SRZ x-intercept / factor is repeated in a given polynomial equation. That's just how many times do you see that root in the equation, or how many times do you see that factor. Now, it's going to be really easy, I promise. So let's look at name the roots and the multiplicity. So when I look at this equation, it's in factored form. Now, if it's in factored form, the exponent tells me its multiplicity. So let's look at our first SRZ. Well, my first SRZ is x minus 2. So since it's x minus 2, that means 2 is the root. Now, how many times does that appear? Well, his exponent is an understood 1. So that means that root or that factor only appears once in your equation. Let's look at our next one. Our next one is x plus 1. So if our factor is x plus 1, that means our root is negative 1. And what's his multiplicity? Well, he's got an understood 1. So understood 1 means he only shows up once. So that's its multiplicity. Now, the last one, x plus 4. X plus 4 means that my root is negative 4, but he has an exponent of 2. So that means his multiplicity is 2, because basically that's like x plus 4 times x plus 4. That factor shows up twice. Now multiplicity is going to play a part in another functioning of the graph, but we'll talk about that here in just a second. Let's look at our next one. He's not in factored form. So to find the factored form, we have to factor it. First thing I see is that I can pull out an x, and then I factor that further to be x times, and then x minus 2 times x minus 2. Okay, so my first SRZ, I have x equals 0 right here. So I have x equals 0. So how many times does he appear? Well, he has an understood 1 as his exponent, so his multiplicity is 1. Now I notice that these two will both produce the same root of positive 2. Well, how many times does x minus 2 appear? 2 times. And that is literally all there is to multiplicity. Now, another fun fact. The multiplicity also tells you if the graph crosses at the SRZ or if it bounces up or bounces down, if it's a bounce or if it's a cross. So, if the multiplicity is even, it bounces. So, if that multiplicity is an even number, 2, 4, 6, 8, who do we appreciate? Then that means your graph is going to hit the 0 and bounce right back. It's not going to go through it. So if your graph is opening down, it's going to hit the 0 and bounce back down. If it's opening up, it's going to hit the 0 and bounce right back up. Take, for example, the quadratic. Here, I have a root at x equals -1, and its multiplicity is 2. So it decreases to -1, hits that 0, and bounces right back up. Now, if your multiplicity is odd, it's going to cross over the x-axis. It's going to go through the x-axis. So again, take, for example, here, it's still x equals -1, but it's got a multiplicity of 1. So look what it does. It goes through and keeps going. So even multiplicity bounces. Odd multiplicity goes straight through. This is going to help us in determining the graphs of our equation. So we know that if the multiplicity is even, it's a bounce. It hits the intercept and bounces. If it's odd, it crosses over, it goes straight through. But also multiplicity affects the performance of that graph at that intercept. So let's look here. Okay, if the multiplicity is 1, so take, for example, here at x equals -2. That means we have an intercept at +2. The multiplicity is 1, so it's going to go through, but did you also know as it goes through, the shape of your graph will look linear. Okay? What if your multiplicity is 2 though? So let's take x, so we have another intercept at +1. +1 has a multiplicity of 2. So remember, it's going to bounce. But did you know if the multiplicity is 2, not only does it bounce, but it looks like a quadratic at x equals 1. Looks like a quadratic because its multiplicity is 2. Now, let's look at our next root. Our next root is -3, okay, and it's got a multiplicity of 3. So 3 is odd, so it's going to go straight through. But did you know that also because it's 3, it's cubic? So it's going to kind of look like a cubic graph as it goes through that intercept. All right, now let's use what we know about the multiplicity to help us produce an even more accurate graph. So if you remember, step 1 is they want us to find the roots. So they gave this to me in standard form, so I'm going to have to factor and solve to find the SRZs. And then we're also going to state the multiplicity because now that we know that, that can help us. Okay, so looking at y equals 3x to the 5th plus 18x to the 4th plus 27x cubed, setting it equal to 0, I'm like, I can pull out a 3x cubed. So I'm going to do that. That leaves me with x squared plus 6x plus 9. I can then factor that further to be x plus 3x plus 3. So let's look at our zeros. If we take this factor right here, 3x cubed equals 0, that means x is going to equal 0. Now it also has a multiplicity of 3. Since it has a multiplicity of 3, that means that's odd, so it's going to go through the intercept, but it's also going to look like a cubic. And then we look at our next one. Our next intercept is -3. Now, that has a multiplicity of 2 because it appears twice. So, since it has a multiplicity of 2, it's going to bounce, but it's also going to look like a quadratic when it bounces. Okay, so we found our SRZs. Next, we have to talk about left and right in behavior. Well, luckily they gave that to us in standard form. So we look at the leading coefficient, or the leading term. Now, we always determine right end first, so 3, it's positive, so that means right end's going to go up. For the left end, we look at the exponent. Well, 5 is odd. Odd means opposite. So opposite of up is down. Then we have to find the y-intercept. That's plug in 0 for x. And luckily it's 0, 0. So our y-intercept is also taken care of by the x-intercept. Then we use our calculator to find the relative max and min. So we'd plug this the top equation into y equals, hit graph, adjust our window, and then do second trace max, second trace min. And when we do that, we find that we have a relative max at -3, 0, and a relative min at -1.8, -25.2. All right, let's graph all that information we know. So, my x's are fine because they fall between -10 and 10, so we're good there. But my y's, I had like a -25.2. So I'm going to scale my y's by 5. So I'm going to put that on my graph so the reader of my graph knows, hey, the scale changed. Okay, I'm going to plot the zeros. All right, now, if I remember correctly, go to the rightmost point, right end was up, and left end was down. Now I'm going to plot my relative max and my relative min. And my relative max was actually one of my intercepts, so that worked out. So that's why if you look at your graph, you can tell what's happening. So here at 0, and it's hard to tell. You kind of have to zoom in at your graph, but it kind of takes on the shape of a cubic. And then right here at -3, it takes on the shape of a parabola. Now, let's review factor by grouping. Now, the reason we're kind of reviewing this now is, hint, hint, on your homework, when you factor some of those guys, you may need to use factor by grouping, and that's okay. So let's review that. So I want to factor 3n cubed minus 4n squared minus 12n plus 16. So if you remember, you underline the first two, underline the second two. Now we're going to GCF the first pair, so that's going to be like an n squared. And when I pull out n squared, I'm left with 3n minus 4. On the right pair, the GCF is 4, but because I have this minus here, I'm going to pull out a -4. So that's going to switch it to be 3n minus 4. Now, here's my common factors. So I pull that out, and when I pull that out, I'm left with n squared minus 4. Now, 3n minus 4 will not factor any further. However, n squared minus 4 is a difference of 2 squares. So I break that into being n plus 2, n minus 2, and now you could factor and solve to get your zeros. All right, so that's it. That's it for the lesson. We're done. You will now go complete your homework assignment 5B.2, and we will see you back for 5B.3. Have a great one, guys. Please make sure you wash those hands, wear those masks, socially distance. Perseverance, this will be over a lot sooner. So make sure you're doing everything that you're supposed to do to stay safe and make great decisions. Bye, everybody.